Just wanted to discuss today's remaining part of the problem. So that is your deflection check. So we have designed the slab. We know the reinforcement details, the thickness. Now we just need to have a check on the serviceability criteria. That is your deflection check. So this is an indirect method of checking, satisfying the deflection criteria suggested by the code. So if you can satisfy this criteria, you can be assured that your deflections will be in limit. So for checking deflection, first of all, you need to identify at which location you need to check that. So this was our slab. If you load it, the deflections will be coming max at center like this. This delta is the point of concern here. We need to limit it, limit the deflection. Okay, so how we are going to do that? So there is a check we are going to perform. Kindly observe this deflection is coming maximum at the midspan. Okay, this midspan deflections are the highest. So this is where we need to check it. So let's check it. So first of all, we need to identify what reinforcement we have provided at the midspan at this location. What reinforcement we have provided. If you see the design that we have done today, we have provided 8 tor at the rate 110 center to center, 8 diabars at the rate 100 mm center to center spacing we have provided at this midspan. So this was our slab. We have provided this midspan reinforcement in this direction as 8 tor at the rate 200, sorry, not 200, at the rate 110 center to center. So in this midspan, we need to limit the deflection. This is the critical zone. So as we know now, the reinforcement provided at the midspan, we need to find out the AST provided for the calculation of this modification factor. So I will tell you step by step how to proceed. First of all, let us just find out the AST provided at midspan. We have designed the AST requirement, from there we have provided. So let's say from the design criteria, design AST, we calculated the spacing. This is how we have done. We first calculated the AST requirement. From there we have calculated the spacing 8 tor at the rate 139 at midspan. This was the requirement, but we have provided what we have provided 8 tor at the rate 110. So the provided reinforcement is little bit higher than the required. So we need to calculate the AST provided at midspan. What is it? How you are going to calculate? So remember that formula, spacing required is 1000 Fi by AST required. This is how we have calculated spacing required. Now we know what is the spacing provided. Now we know the spacing provided. So once we know the spacing provided, we know the bar dia that we are using, we can find out AST provided. So AST provided will be 1000 into Fi by spacing provided. This is how you have to find out AST provided. So if you do this calculation AST provided, it will be 1000 times multiplied by 1000 times multiplied by area of 18 mm dia bar is 50.3 divided by spacing provided is 110. This one, this one. So what is the AST provided at midspan? It is I think coming 457 mm square per meter. Right, 457. 457 mm square per meter. This is the AST provided at midspan. Correct. Remember this. Now let us calculate. Once we have the AST, let us calculate the percentage of reinforcement. Because see, finally we need to find out the span by effective depth ratio, maximum allowable, and we know the basic value. We need to modify that with the help of modification factor. And to calculate modification factor, we need percentage of steel, percentage of tensile reinforcement, and area of steel required and area of steel provided. These two informations to calculate modification factor. Let us calculate the percentage of steel. So initially when we were calculating, we have taken 10 dia bars, so the effective depth was different. So if you remember, the clear cover was 30 mm for moderate exposure condition. Let us once again calculate the effective depth for the new reinforcement that we have provided. It is 160 total depth minus 30 minus 8 by 2. Your effective depth becomes 126 mm. Okay, just a minor change. So let's calculate percentage of tensile reinforcement. It is 100 AST by B into effective depth T. This is how you need to find out the percentage of tensile reinforcement. If you work out this problem, just put percentage of steel calculation AST provided, this value. Just this value, you provide it here. You will get percentage of steel as 0.36. Okay. So one more thing you need to calculate. It is your FS, service stress of steel. Based on these curves, we need to select whatever value we get. Based on this, we need to select from these curves that are given here. 120, 145 FS value. Let us first find out what is our FS value in this case. So our FS will be 0.58 Fy times AST required by AST provided. Okay, just calculate 0.58 times Fy is Fe415, 359 by 457 required by provided. Your Fs comes out to be 189.6, roughly 190 Newton per mm square. This is your Fs. So just remember these two values. Your Fs, this Fs value and this percentage of steel value. Okay, just write it down here. Your percentage of steel tensile reinforcement is 0.36 and Fs value is 190. Now we have these two values. Now using this chart, figure 4, IS 456, page 38, we need to calculate the modification factor. How we are going to calculate this? Let's see. What is the percentage of steel? 0.36. And what is our Fs? 190. So we have, so this is actually matching. So this is This time this is matching, but every time it cannot may not be matching with the curves given here. You may need to interpolate. So let's say we have FS 190 here. This is our curve from where we need to find out modification factor. And percentage of steel is 0.36. So this is zero point 0.2, this is 0.3, and 0.36 will be somewhere in between 0.3, this point and this point. So it will be like somewhere here, right? Let's draw a line. So this is what it looks like, and let me highlight our line. So this is our FS value. This is our 0.36 percentage of tensile reinforcement. This is coinciding here. So from here, look at your left, come to the vertical axis, you will get one value. So this is your modification factor. So see, this is 0, 0 0.2, 0 0.4, 0 0.6. It's in the interval of 0.2. So it will be 1.8. So at the center it will be approximately 1.7. So you can take it approximately 1.7, and somebody can take 1.75 also. Okay, so there is a little bit confusion here. Exact value is not like visible to us. So there is little bit approximation you have to do. So we got our modification factor KT as 1.7. Let's take it at 1.7. Always try to take the lower value for being on the safer side. Once we have it, now we can calculate L by D max. What is the L by D max for our slab? It is L by D basic value multiplied by KT. We know initially we have assumed this basic value of span to effective depth ratio multiplied with modification factor. How much it will be? 23 multiplied by 1.7. It will be 39.1. So this is your maximum allowable span to effective depth ratio for our for our one-way continuous slab, or the end span, what we have designed in the class. And what we have provided, now we have to check what L by D we have provided. So what was the effective span for the end span case? It was 3463, and effective depth just now we have calculated, right? But it is 126. 126. This coming out to be 3463 by 126, 27.5. So this is your L by D provided. So you can clearly see that your L by D provided is less than the L by D max. That is the allowable limit for our continuous one-way slab. Okay, so hence this is safe. Our design criteria is satisfied. Everything is safe. We can proceed with the detailing and the construction. So I hope you understood this calculation. So basically what you have to do, you need to calculate L by D max, maximum allowable span to effective depth ratio, based on whatever reinforcement we have provided after the design and whatever service stress of steel that is coming from our design calculations. Just calculate the modification factor Kt, multiply with the basic value, we'll get the L by D max. Next, calculate L by D provided. Whatever effective span we have in our slab, this is what we have provided actually in our slab, and the effective depth that we need to calculate after providing a new reinforcement. If it is not, if we have not changed the reinforcement, then there were no requirement of changing the effective depth. So we have changed the reinforcement at last. I think initially we were using 10 tor bars, so it was kind of uneconomical. So we changed to 8 tor. So kindly calculate the effective depth once again and calculate this effective span to effective depth. This is your provided value, this is your maximum value. You can see that the provided value is way lesser than the maximum value. So from this check, we can see this is too much safe. We can even reduce the depth of the slab from, I think we have taken 160, right? You can do the same problem, exactly same way. Just start the problem with a depth of, I would say 130. Just do not do the starting calculations where we have assumed the depth on the basis of this LYD values. Now we have done on design calculation. Now we know what depth it can satisfy the design. Now we can just check it by starting with 130 directly. We do not need to find out any depth now. Okay, so this is how we can do. And just one more thing to check these things again and again, like this trial and error 160, 150, 140, whatever you want to do. So this time you need to prepare on Excel sheet. It will be very helpful for you. Okay. So I hope you have understood this modification factor calculation from figure 4 uh, of IS 456 and how to, kind of check the detailing deflection. So if there is any problem calculating the modification factor from this chart, you can have a look on this table. Sometimes it gets very difficult to calculate the modification values from that, chart, because it may not coincide every time. Like this time we have got fs value as 190, but we can get somewhere in between this also. Let's say our percentage of steel is not exactly 0.3, 0.4. Let's say our percentage of steel is 0.45. So for 0.4 you need to find out the intermediate value first. Then for 0.5 you need to first find out the intermediate value. Then for 0.45 you need to interpolate between these two values to find out the modification factor for 0.45. So 2-3 times you need to do the linear interpolation. So this may be little lengthy, but you should do it for accuracy. Anyways, this chart I will share in the group. This is very helpful. You can refer to the Pillai Menon book. Everything is given. That's a very good, nice book. So you just go through the lecture notes that I have provided and try to understand. And please check that video that I have provided. I strongly recommend to have a look on that video. Go through that. And if you have any doubts, you can ask in the group. Okay, that's it. Bye.